Welcome to Privacy Preserving Data Sharing for Medical Research. I am Jonathan Hochman, and my co-authors are Michael J. Fischer and Daniel Boffa. Electronic patient medical records contain vast amounts of information of potential value to researchers striving to understand diseases, treatments, and outcomes. The effective use of such data, however, is limited by privacy concerns. In particular, in the United States, privacy laws require the removal of personally identifiable information from any medical data that is released for research. To be most useful, the data from different providers for the same patient needs to be linked together. This paper applies cryptographic techniques to the problem of privacy-preserving linking of medical records. The paper has three parts. First, we describe the problem in the field of medical research. Then we introduce a new cryptographic primitive, which is used to design a system and a protocol for performing privacy-preserving record linking. The medical research problem has a number of constraints. First, personally identifiable information may not leave the domain of a healthcare provider. Complex medical conditions may require treatment by multiple providers, including conditions like cancer. Medical research databases, as a result, are fragmentary because they often don't collect the full picture of information related to a patient. So our question is, how do we link anonymous sensitive information about the same patient coming from different healthcare providers without using any PII or any identifier that is equivalent to PII? First, we will define a new cryptographic primitive. So if X is an identifier used by a data provider H to identify an entity, we let B of X be a one-way hash function. A blinding completion pair for provider H is a pair of one-way functions B sub H of X and C sub H of Y, such that when these functions are composed, when the completion function is applied to the result of the blinding function, the result is B of X. For all H, B of X will produce the same value. So first, a little number theory. We're going to use prime numbers P and Q such that P equals 2Q plus 1. These primes are commonly used in cryptography. P is called a safe prime, and Q is called a Sophie-Germain prime. Interestingly, Sophie Germain was a brilliant French mathematician over 200 years ago. Because she was a woman, she was not allowed to study mathematics at university. Instead, she studied in her family library, and she established an anonymous correspondence with her advisor, Gauss, and she used the pseudonym Monsieur Leblanc. And eventually, she did tell Gauss that she was a woman. After making many great discoveries in mathematics, very sadly, she died of breast cancer at age 55. And this is exactly the kind of outcome that we hope our system can help researchers to avoid. We're going to use generators. A generator is a primitive root of the set Z star P, which are the natural numbers relatively prime to a number P, numbers up to P. And for every number in Z star P, that number A can be expressed as G to a power K mod P. And we call K the discrete logarithm of A modulo P. So that's what a generator is. The discrete logarithm problem is that given A equals G to the K mod P, finding K is computationally impractical as far as we know, if P is a large, safe prime. If P is not a safe prime, there is a risk that P minus 1 might have many small factors, and when this is the case, there are some potentially practical attacks against the resulting crypto system. So we're going to use discrete logarithms to build our blinding completion functions. We need to use Eulers totient function, phi of n, which is equal to the number of elements in z star n that are relatively prime to n. In the special case of n being a prime, then phi of n is equal to n minus 1, because obviously n is prime, so all of the numbers up to n will not divide into n. Euler's theorem states that for a in z star p, a to the phi of p mod p equals 1. We are going to make use of this shortly. So here are how the blinding completion functions are constructed. This is a simple way to construct them. We believe there are much better ways available too. But for ease of explanation, this is our proof of concept. First, we choose two random numbers, r and u, in z star phi of p. We then choose a value v such that u plus v mod phi of p equals r. And then we define the functions as follows. B of x is x times g to the r mod p. B sub u, the blinding function with the secret key u, is equal to x times g to the u mod p. The completion function c sub v, a secret key v, is equal to y times g to the v mod p. And we then see in the final row, the math, that the composition of the completion function applied to the blinding function will result in the hash function b of x, which is the same regardless of the value chosen for u. So before I describe the system design, these are some of the important elements of the system. We are going to use security nodes to isolate medical providers from cryptographic functions and secret keys. We have security nodes that are going to perform these functions via an API, by a remote call. We cryptographers don't necessarily trust medical providers to be competent at doing these kinds of calculations. Naturally, the medical providers don't trust us to be competent at performing surgery. So we are hoping for a system design which lets each specialty focus on what they're good at. We're also going to use pseudonyms. We're using blinding functions to generate a unique pseudonym for each patient at each healthcare provider. And we are using completion functions to do the privacy-preserving record linking. The completion function will process a pseudonym and turn it into something that is anonymous but the same for each patient, regardless of which healthcare provider is submitting the data. So we have two different kinds of pseudonyms. We have one called the LPID, local patient identifier, which is used by each healthcare provider to share anonymized medical data with the medical research databases. We have an APID, or anonymous patient identifier, used by the medical research databases to join anonymous data about a patient coming from different sources. So the relationship between the identifiers is defined by math. So we start with X, which is some kind of commonly used identifier, such as a social security number or a name and birthday pair, which can be canonicalized to account for misspellings or alternate names, X is likely to be PII, so X cannot be released. We create Y, which is a standard secure hash of X. Y could be released, but we don't want Y to be persistent data in other parts of the system, because if there's a breach, someone can gather a large amount of data and they can start guessing values of X by hashing and see if they find any matching record in the data set. The healthcare provider is going to send this hashed value Y to its security node, and the security node will perform the blinding function and return an LPID. When data is contributed to the medical research database, that LPID is going to be communicated to the database's security node, which will then calculate an APID. And the database will be able to use the APID to link records. We have proposed a workflow. So each healthcare provider will be assigned a random value of U and have a unique blinding function B sub U. The healthcare providers will obtain a unique LPID for each patient by querying their security node, which holds the blinding function B sub U. When contributing anonymous medical data to the research database, the LPID is converted to an APID by the database's security node using the completion function C sub V. And even though the LPID of a patient is different at each healthcare provider, the APID derived from the completion function will always be the same, which is the property that allows us to link records in the database. So medical data will flow through a separate pathway. The medical data will be sent directly by a healthcare provider H to a research database D without any identifiers. We simply generate a random transaction serial number and attach that to the source, the destination, and the medical data, and send it along. There is then a separate data flow from the healthcare provider that includes the identifier. The provider will send the transaction serial number along with the source, destination, and the LPID to its security node. The security node will check signature on the message to ensure that the healthcare provider is sending a valid authenticated message. The security node will then pass this identifier message along to the security node of the database D. Upon receiving that message, the security node of database D will use the completion function C sub V associated with healthcare provider H to calculate the APID. And then the security node will send the database the transaction identifier, the source, the destination, and the APID. The database can then match up using the transaction serial number T and add the data M to the database with the APID identifier. If the APID matches an existing record, the new data can be linked to the existing data and thereby provide a more complete view of the patient's healthcare. So our network looks something like this. We have healthcare providers on the left. There are orange security nodes, which could be independent service providers, or they could be operated by a healthcare provider if that healthcare provider has sufficient expertise. Likewise, research databases on the right could, in theory, operate a security node of their own, or they might rely on a third-party security provider. So, in addition to the system we have outlined in the paper, we have also proposed some additional security features. One feature is that the keys U, V, and R are rotated periodically. So the key rotation ensures that if there's been a data breach and some data leaks containing an LPID or APID, those values will change over time whenever the keys are rotated. So this causes any leaked data to become obsolete and unusable over time. The other interesting property of security nodes that we propose is that these nodes will only communicate with other security nodes or their client systems that are on an allow list. And this helps the security nodes to be an order of magnitude more resilient than a server that is exposed on the internet, which could conceivably be attacked from multiple sources. The security nodes can also utilize hardware security modules so that the secret keys can be kept in a separate subsystem, so that even if a security node is compromised, the secret keys are not leaking. We have identified several areas for future work. I'm going to briefly highlight some of them. The blinding completion functions that we have proposed rely upon a generator and multiplication. This can lead to some potential security risk because if an LPID and APID are discovered, the ratio between them is the same. A better way to do the blinding completion functions would be to encode the message and exponentiate it with the blinding function and then exponentiate it with the completion function. We've thought about how to do this. We haven't explained it in the paper because it's a little bit more complicated, but I believe that it will be possible to design more secure blinding completion functions in the future. We are also working on building a prototype system because we have to demonstrate how this would work and try to recruit healthcare providers to try it. And finally, we feel that it will be necessary to describe the security guarantees of the system and its failure modes. In other words, what happens when there's a breach. The description of these security properties should be more granular, and of course this will depend upon some of the ultimate design and engineering decisions that go into the implementation. Thank you very much for watching our video, and I hope that you will read the full paper. Please do contact us with any questions. Our email addresses are in the paper. Thank you very much.